All right. Intro to Space Navigation, Spring 2025, Lecture 20. I'm sorry, I glanced down at my notes and I was looking at a future lecture. This is Lecture 18, let me be clear. Lecture 18. And we are resuming our trackers screen here. So, maybe clarify. So, this is our 4-lecture unit on star trackers. Really, it's 1.5 lectures on the space camera as a navigation instrument. So if you have, for example, a starfield image, we as navigators don't really want the pixel values where the stars are. We want vectors in the camera frame to where the stars are. So we need to talk about how to go from pixels to directions. And that involves image processing to even find the pixels that correspond to stars, and then discussing the geometric relationship between pixels in an image in 3D space. That was lecture 16. Lecture 17 is, okay, if we're trying to navigate using stars, then we must have some sort of a star map, right? Navigation requires a map of some type. Generally, you're not going to be able to navigate without some atlas of where all the stars are, which used to be, a giant book that the ship's navigator would carry around with, other numbers and parameters and such. And the more modern equivalent would be, okay, here's a catalog of where the stars are. We talked about Hipparcos. Hipparcos is a list of approximately 118,000 stars with all of their right ascension and declination angles and other information that you need to reconstruct. Okay, where would I find this star in the inertial frame? Okay. So then naturally today, we actually have what I consider to be the hardest part of the problem. However, fortunately, it is a shorter lecture, so hopefully we'll get you out of here in less time than usual. This is the data correspondence problem. This is, okay, I found an image with 3 stars. Which 3 stars are those out of those 118,000 that we just talked about from the Hipparcos catalog? That is a non-trivial problem to solve. And then once you know, okay, these 3 stars in the camera frame are these 3 stars in the inertial frame, and I'm sure of it, then you're on to Waba's problem, which is lecture 19 day of this week. And Waba's problem is just determining the direction cosine matrix from frame A to frame B, given vectors that you know are the same vectors, just expressed in 2 different frames. What we'll find is that Waba's problem, the lecture is going to be pretty math heavy, but when the time comes to actually sit down and code it up for your assignment, it's going to be pretty straightforward. So don't be frightened of Waba's problem. I would say be the most frightened of the index search logic that we're going to be talking about today, because I think that's going to be where, at least speaking personally, my background is in mechanical and aerospace engineering, not computer science. So I tend to struggle with stuff like this. Maybe, depending on your background, you could probably code up a faster star tracker algorithm than I can. I had students last semester who could outperform me in terms of total runtime from startup to attitude. They could get it done quite a bit faster. So I encourage you to be creative in the way that you do this part of the problem. But the rest of it is pretty straightforward. So image processing to get your vectors, there's kind of an established way to do that. Determining the line of sight directions using the standard model and the inertial camera or in the inertial frame. We talked about that. Lecture 18, I'm going to kind of lay out the problem for you, and then there will be part of it that you need to kind of sort out for yourself. And then finally, lecture 19 is the attitude determination, which is, it's not 1 line of code, but it's certainly less than 10. It's pretty straightforward to put this together. Okay, so I'm known for kind of beating it to death, my review before we start lecture, but I think it's important to go back and give context to what we're going to talk about today. So today is the star identification index search problem, and let me preface this with a question here. So today is star identification. Okay. So we know in order for a measurement to be useful for navigation, we have to know what we are measuring. In the case of stars, we seek to correlate image stars with catalog stars. So let me ask this question. Some of you might know the answer to this already. I'll be impressed. But I also like to hear people who aren't sure kind of puzzle through it. Um, how would we go about identifying the stars in our image? Anyone want to take a guess at it?
Could you go with
feel
like
like
the old-fashioned, oh, sorry, old like navigation where you would find something like so reliable like the the polar star and then go from there with relative positions around it?
Okay, so I like that. I'm going to be tricky now. Actually, here, I'm going to just copy paste this first shape. So start with the star that you can identify and then work around it. But then I would turn that around and say, okay, how do you identify, like, how do you identify that one?
use like brightness values. So
Ooh,
if
Do
you
you have
know,
like some?
sorry, I got a couple of different ones. Let's do, so Catherine, you had something, and then we'll go back to Michael.
using brightness values. So if you have the brightness values of each of you have the brightness values of each of the stars in some of the tables. So if there are certain unique brightness values, then that's how you can identify the first star.
So brightness is not bad. Now that would require photometric calibration, which we didn't quite talk about yet, but that would be the relationship between the number of photons coming out of the star and the apparent brightness in the image, which is different than the geometric calibration that we talked about before. The tricky thing there is that a lot of our cameras are not going to be sensitive enough, right? Because you might say, well, we can identify this star because it is exactly this bright. And then, okay, well, what pixel value should we be looking for in the image? Well, remember, there's only 255 pixel values for an 8-bit camera. So we might not have the sensitivity to do that type of detection. But
Could
that's not a
you
bad idea.
could you use colors like using Doppler shift to tell which stars you're looking at by their velocity relative to you?
Ooh, so okay, so now there's two things you just mentioned. So color makes me think of like their spectral response, right? So like what is the intensity of that star as a function of light wavelength? Which is a fine thing to do, but that's not what this sensor is. And by the way, that is the most common thing when I ask people, like, oh, well, how would you identify stars? Color is number one, typically what people come up with. Though what we're actually going to do in this class is probably something that you would think would never work, and it's actually pretty darn good. But color wouldn't work with a camera because star trackers are black and white cameras, so that's out. And even if it was a full color camera, generally what you would need is a spectroscope or spectrograph, something that basically refracts like a prism of light onto a focal plane array and then takes that sort of image. That's fine, but that's just not what this instrument is. And then to your other point, detecting velocity, not bad, not a terrible idea. Here's the tricky thing, and I think people are getting really close. I'm going to give you a hint. And this is my best art, so wish me luck. Can you identify these stars?
Relative positions. That's Orion.
That's Orion. Yep. So how did your brain just do that?
Well, I saw
Despite
three stars.
despite my suboptimal artwork, you still found it.
I saw 3 stars in the middle and 4 stars in the corner.
Yeah.
And I
Okay.
know, that particular asterism is
Very good. That's also our word of the day. So good on you. Asterism is a group of stars, which is not necessarily the same thing as a constellation. Constellation is like an established group. So Orion is a constellation, but you could just pick any 3 random stars, and that's an asterism. The same way that like geese make a flock, the stars make an asterism. So you determine which stars these are by shape, and our brains have an amazing ability to detect shapes and patterns, which is why the whole sky is covered in these constellations. Which a lot of constellations, I have to admit, I would never have came up with that. Like the idea that Orion is a hunter, it's not clear to me, but I'm glad that somebody thought of that. So this is a recognizable constellation. Okay, now let's look at the other extreme. How would we identify this star? Yeah, this is meant to be a trick question. You're toast. This is impossible. Using the data in a star field image, just one star floating in space, it's like, well, you might say we could determine its brightness, but then we know that our camera hasn't really been photometrically calibrated, and even then it doesn't have the sensitivity to go off the brightness. If you're just using pixels in an image, like, oh, these are the bright pixels, you're done. You're not going to identify that star. But I would contend that if you had 3 stars, you could work with this. That this would be enough to get you something. More would be better, but this would be something. Because this actually has some data. So what data is there in this image to identify these stars?
Vectors between the stars?
The vectors between the stars. I like that. So I said before our word of the day was asterism. I guess we have 2 words of the day because the other word of the day is called invariant. And I'm going to write this all down later. For now, we're just yapping. An invariant is something about these stars that is the same, so it does not vary, depending on how you look at it. So imagine that you said, okay, here's a star, and I know that if I look 15 pixels to the right and 14 pixels down, I'll find another star. And then if I look another 14 pixels down, whatever, it's like counting the pixels between stars would be a mistake. Because what if this whole thing rotated? What if your camera was positioned a different way, right? So the absolute position of stars in your image can't be invariant. However, the shapes that stars make are invariant. Now we recognize this shape. If I rotated this a certain way, then the relative configuration of these stars is the same. And if you picked up your camera and moved it to Jupiter, the relative configuration would still be the same. Now it would be slightly different because of parallax, but for inside the solar system, we're going to say that the shapes of constellations don't change. And what is actually the same between these stars is the vectors between them. Well, I'm going to draw a picture later, but it's the angles between them are invariant. So this has what I'm going to call more data. This has 3 interstar angles. And we can work with those angles. And then I would contend that you have at least a chance of identifying 2 stars because this still has some data. This has an interstar angle. So you figure for 2 stars, I and j, there's theta ij. For 3 stars, there's theta ij, theta jk, theta ki. Right? And then for an even larger constellation, you'd have even more interstar angles that you can work with. And so we're going to be using interstar angles for star identification in this lecture. And you might be thinking, gosh, it sure seems to me that there's going to be a lot of triangles of stars that have basically these 3 interstar angles. And the answer is, well, yes, but actually no. Right? There will be exactly one set of stars with exactly these interstar angles. Now, the problem is how sensitive is your detector and how cluttered is your database, because you might have a risk of false positives if you have an overwhelming number of stars. So we'll get into the gory detail, but for now, just wanted to get the vibes across. We are going to navigate using interstar angles. So here come the notes. So in much the same way that humans can recognize constellations, not individual stars, it is possible to recognize an asterism or group of stars in a star field image. This requires asterism descriptors which are, word of the day number 2, invariant to changes in spacecraft state. So the angles between stars are the same no matter how you look at them. If you spin your spacecraft around, if you look at it at some weird angle, some glancing angle, you're still going to get the same angles between your stars. So these asterism descriptors are called invariants. And they can be thought of as numerical name tags. So then the question, which I kind of spoiled this already, is what about an asterism is the same no matter how you look at it? We'll say regardless of viewing geometry. If you have 2 stars, they will have some interstar angle, which will be the same even if you rotate your camera, even if you pan up or down or you zoom or something like that, you're always going to get the same angle between the stars. Not necessarily the same pixel count between the stars, because remember, our camera has distortion. Sometimes it has these weird nonlinear effects. So we're not counting pixels. What we're going to do is star number 1 from pixels into a vector, star number 2 from pixels into a vector, and then dot product those vectors. That's going to be our strategy. Now, if we have 3 stars, we have 3 interstar angles, or 3 dihedral angles. So you can actually use different angles to identify the stars. It does not need to be interstar angles. The big thing is that there are 3 pieces of information about 3 stars that is their name tag. There is 1 piece of information about 2 stars that is their name tag. So let me draw a quick picture for you here. Let's say we have our camera here. Let's be fancy and make this a rectangular prism. And there's our camera. Okay, cool. And let's say that we've got our image here. Okay. And then we've got some star out here, some star out here, and some star down here. Okay. And let's do Yeah, okay, let's do it like this. Yes, I see hand up. Is that you, Peter?
Oh, sorry, I forgot to put it down from earlier.
Oh, I see. Okay, sorry. I was worried I was ignoring you. I was not trying to do that. Okay. So let's see. We've got 1 star there. Star there. Okay, you know what? All right, there it is. And we've got star there. That'll do. And in the image, let's do it this way. We can compute information about these 2 stars, which would be related to this angle between the vectors, theta, I, j. We can also compute information about these 2 stars, which is going to be like this. So this is going to be star, I'll get my diagram right, star I, star j, star k. There we go. So this angle here be theta j, okay? And then in green, information about these 2 stars, this would give us theta I, okay? Where this is our camera, this is our image, and these are our stars. So before we move on, think about degrees of freedom. A star field image with D stars has D pieces of information. Sorry, 2D pieces of information. You figure you've got the azimuth and the elevation to every star in the image. So if there are 5 stars in the image, then you have 10 pieces of information from a navigation standpoint. Okay, so then a camera, which is free to rotate, has an attitude, unknown attitude, with 3 degrees of freedom. So therefore, an asterism seen by a lost camera has 2D minus 3 invariant properties. Okay. So what do I mean by that? 2D minus 3. So you figure you've got your information, which is almost, you can almost think of it in terms of like income and expenses, right? You've got your income, which is going to be 2D pieces of information. Your expenses is that you don't know your orientation, which is 3 degrees of freedom, right? We'll pitch into you on. So then you have 2D minus 3 bits of useful information, or in this case, invariant properties. So for a single star, 1 star, that is 2 times 1 minus 3 is less than 0. So there are no invariants, which is what I was saying before. If we're trying to use interstar angles and there's 1 star, you're cooked. If there's 2 stars, then you have 2 times 2 minus 3, which is equal to 1. So there's going to be 1 invariant. That's that interstar angle that we talked about before. If there's 3 stars, then it's going to be 2 times 3 minus 3. Sorry, this is a dot, and then this is a minus. I want to be more clear about that. That's going to be 3, or 3 invariance. And so on and so forth. Okay, questions up to that point, or are we tracking okay? Okay, cool. Let's keep pushing. So next is star identification as an index search problem. So we're heading in the direction of setting up and querying a database. So the problem of star ID then becomes an n-dimensional index search problem where n equals 2d minus 3. So if you're trying to identify 2 stars, you're doing a one-dimensional index search problem. So you basically just have a list. You can imagine creating a list of, okay, for all possible pairs of stars in Himparco's catalog, here are their interstar angles. You might imagine that that's going to get pretty busy pretty quickly, and that number line is going to get, basically it's going to be crowded. And so that means that, and we'll draw a picture of this in a second, but the lower dimensionality of your search space, the easier the index is to build, the easier it is to search, but the higher your risk of a false positive. It's like, here's 2 stars that are exactly 17 degrees apart from one another. It's like, okay, well, here's another pair of stars that's 17.01 degrees apart from one another. Are you really sure which one is which, right? So you have some problems there. Whereas if you're working with a triad of stars, then you have a 3-dimensional search space problem. So you're looking for a nearest neighbor in 3D space. Things tend to spread out as you offer more dimensions to the search problem. Right? So that's kind of the point that I'm getting at here. One can try to identify larger or smaller asterisms. And so lower dimensional spaces can be searched more easily. And higher dimensional spaces are less crowded. So for example, if you choose star pairs, then you have one invariant. And your index is a number line. If you choose star triads, you have 3 invariants. Your index is 3D space. And then as you increase in dimensionality, you have a less chance, a drastically less chance of false positive. And so when you actually do your index search and then your search your hypothesis validation and all that, things start to blur the line between art and science, as we'll find. So to be clear, if you've got a camera, you know what? I actually don't like the little autocomplete thing. I know I've got my crummy rectangle, but I'd rather it just be my crummy rectangle. And then you've got star number 1, star number 2, star number 3, line of sight, line of sight, line of sight. This is star I, this is star J, and this is star K. And we said before we liked red for theta ij, liked blue theta jk, and we like green for theta ik. Well, we can think of this as an n-dimensional search space. Let's try that again, where this is theta ij. Okay, this is theta jk. And this is theta ik. And you can imagine entries are points floating around in 3D space. And you might say, okay, I've computed 3 interstar angles based on the information in my image. And that tells me that I'm probably looking in this region. And you say, okay, I'm really pretty sure that my star is in this sphere. So you end up with a search region problem. You're saying, okay, somewhere near here has got to be where my star is. And you see, oh, look, there is one. As I search my index, there's a triad of stars which is very close to my initial search. And so there's always going to be some noise, some error on your interstar angles that you identify in your image, if for no other reason than because we struggle to get a perfect centroid out of our stars, right? And then whatever other information, kind of whatever other perturbing effects stop us from getting a perfect answer. But you go, well, look, here's the best guess in the catalog. I'm really pretty sure that the triad I'm seeing in my image is the triad represented by this point in the 3-dimensional index space. So assuming those 3 stars are these 3 stars, let's go solve Waba's problem and be done with it. That's the basic idea. So, well, we'll pause for a second. There's other considerations, but that's the high level idea. Is that making sense for everybody? Any questions? Cool. All right. So you might say, so let's just take all triads of stars and make an index. And I would say, not so fast. We're going to run into a problem real quick. This might have occurred to you. There's 118,000 stars in the Hipparcos catalog, and we need to pick every set of 3 from that. So a catalog of capital M stars and an asterism, or sorry, yes, and asterisms of D stars produces an index of M choose D, right, in terms of combinations, invariance. So let's put numbers to that. In the case of the Hipparcos catalog, and star triads, that is, remember, it's 118,218 stars, choose 3, is 275 trillion catalog entries. And we're not searching them. That's not going to go very well. So what can we do? Well, we don't need to consider every star or every combination. So when you're building your index, this is something to do on homework 4. You'll need to take your star catalog, which you can just download from online, grab the Hipparcos catalog, create a CSV file with all the asterism information, or all the astrometric parameters, I should say. Then you'll need to say, okay, I'm going to put a limiter on my apparent visual magnitude, because we said before that our cameras are not infinitely sensitive. You're simply not going to see a magnitude 10 star with your camera. That's not going to work. So what I would recommend is limit to stars with visual magnitude less than or equal to 5.5. That's the cutoff I did when I was coding this up. You could pick a different number. What'll happen is if you consider only brighter stars, you'll have an easier time searching your index, but you do run the risk of just not being able to see enough stars. Like if you limited yourself to only magnitude 2 and brighter stars, there's not that many out there. Right? As you go dimmer, your catalog fills out, so you've got a much better chance of being able to solve the problem. But then also your catalog gets crowded at the same time. So having a dense catalog is a blessing and a curse at the same time. You could also limit to asterisms that fit in your field of view. Let's say you have a camera with a 20-degree field of view. You are never going to see an asterism where any one of the 3 angles is greater than 20 degrees. So one example is, I would say, that consider only triads with theta ij, theta jk, and theta ik all less than 20 degrees. Or you can even go smaller than that. You could say, oh, I'm going to build some fudge factor in there. I want only interstar angles that are less than 15 degrees. Right? It's up to you. This is where I'm going to give you some leash to do what you want to do on this homework assignment. But it's up to you to fine tune your index to come up with a combination that is reasonably searchable. And before we move on, a few other words of wisdom. So data structures such as the KD tree, the R tree, and the NDK vector can be used to facilitate faster searching. So once you have a match hypothesis, so this is a candidate asterism index match. It can be validated by testing additional stars. So here's, you could pick a new triad consisting of 2 of the original 3 and a new third. And then identify that triad. And then say, do the duplicate stars. Have the same ID. So you could say, okay, I've built up a triad. I've searched the index. I like it. In order to validate my match hypothesis, here's another triad. So instead of stars A, B, C, let me try stars A, B, and D. And then you match those to your catalog. If you find a completely different set of 3 stars, something has gone wrong, right? Because in your image, you used 2 of the original stars and then a new third one. So let's say that you've got catalog or image stars A, B, and C matched to catalog stars I, J, and K. Then if you do image stars A, B, and D, then you had better see I and J or I and K or J and K among whatever other match you get. Hopefully that makes some sense. So this is one method of identifying stars and validating your hypothesis. Or another one which you could try is compute an expected attitude from your first triad. Then project the catalog into the image. Using camera attitude plus intrinsic and distortion parameters. And if you do this, then many, not necessarily all, many stars in the image should be almost on top of their catalog counterparts. So this is actually my preferred method of star identification, is I'll say, okay, I found a triad that looks reasonable. Let me just finish the problem. Let me go all the way back to beginning of lecture 16. Let me solve Waba's problem. Let me get an attitude. Now I've got a hypothesis for the which way my spacecraft is pointing. Now I can take the whole dang star catalog, all 118,000 stars, and see what pixel value they would each have. Like if, it's almost like you're coding up your own little planetarium. It's like, oh, based on this camera direction, I should see stars on all these pixels. And then just look, like, do you see stars on all those pixels? If they line up nicely, then you're in good shape. And if they don't, then you're in bad shape. So that's, either one of these would work just fine. And I'll mention that one of the most popular star ID algorithms is called the pyramid algorithm. Which is a slightly fancier version of this first one I was talking about. So there's some cool, actually there's a great paper you can go and read. One of my coworkers is actually one of the co-authors on the paper. and you can read about some of the methods of star identification that are used on real star trackers. In our class for this project, you can code up either one of these two, and that'll work just fine. So ordinarily we would stop here. I think I do still have a decent amount of stuff to talk about after the break, but this is a nice natural pausing point. So let me say it's 6:50 for you. Let's take a break for 5 minutes, and we'll come back at, it's basically 6:51. So let's say 6:56. And we will continue with what should be a short after break topic. All right, welcome back, everyone. Let's see. So I'm going to go through. I'm just going to erase this bit. Okay, so we're most of the way through our notes for the day. Want to cover one or two more short things. The first, which I think people will find interesting, practical notes for homework 4. So you might want to refer back to this if you're feeling yourself getting lost. This is what I did. It worked for me. So as a reminder, homework 4, I'm going to give you a star field image. This has already been posted if you want to take a look at it. At least I believe it has. I'll have to go through and check. I'm going to give you a star field image. I'm going to give you the camera parameters that we talked about in 2 lectures ago, and you'll be asked to tell me the orientation of the camera with respect to the inertial frame, and then which stars are all of these. And that's basically the whole problem. And so you'll need to go through and be able to process the image, to find stars, to determine the line of sight directions to those stars in the camera frame. And then from there, you'll also need to go and download, and I include a link in the homework assignment, go and download the Hipparcos catalog and work that into an index that you can search. And that's kind of what I want to talk about right now, is that index creation and then index search bit. And then after that, you'll need to validate your match hypothesis and then finally solve Lava's problem. I highly, highly, highly recommend that you work in groups of 2 or 3 or even 4 and break up the work and do it in parallel to the extent possible, because I think this might be too much for one person to do in the time that I've given you. So please do not try to solo this homework assignment. And if you feel like you're a little bit lost, you're not sure what to do, if you're by yourself and you don't have a project partner, let me know and I can try to partner people up. Here is what I did. I recommend that you create a star pair index. Because the star triad index is going to be kind of tricky. I still think you should try to identify star triads, but I think you should do it using a pair index. And be clever about your search. So catalog where each row, I just made a giant table where each row consists of the Hipparcos identifier, HIP, for star I, the unit vector according to I transpose, so that's going to be 3 entries, the Hipparcos identifier, HIP, according to star J, the unit vector of star J, transpose, and these are all in the inertial frame, and then theta I, J. And there should be no duplicates, right? So star I and star I, we wouldn't bother with that, right? It would only be distinct pairs. That's the idea. Where we only look at stars with visual magnitude greater than or equal to 5.5, so brighter than 5.5. Or sorry, I knew I had that backwards. Less than or equal to 5.5. And interstar angles less than 20 degrees. So this will drastically limit the number of star pairs that you can consider. And then the question is, how come on now. Sorry, my autocomplete's getting a little bit overzealous. How to identify a triad? By looking star pairs. Well, imagine you've got in your image star A star B, star C. Then I would say search the index for an angle similar to theta AB, and then keep several pairs, because you won't just get one star pair. If you compute theta AB and you look in your index, if you do a nearest neighbor search, you'll only return one, but I recommend that you return all within some tolerance. So keep several pairs within some tolerance, and then repeat for theta BC and theta CA. And you'll get reasonable, what's the word I'm looking for? You'll have a hypothesis. You'll say, okay, I think stars A and B could be this star and this star, or it could be this star and this star. You'll get several different possibilities. And then you go, okay, I think stars B and C could be this one and this one. But then I think stars A and C could be this one and this one. And then you can essentially whittle down or narrow down possibilities, possible matches, by looking for stars common to all pairs. So you say, okay, I found two stars that are a reasonable match for A and B. And then I also found two stars that are a reasonable match for B and C. And there's a star in common between them. Well, that has to be the identity of star B. And then I found a reasonable match for A and C. And one of the stars matched one of the stars from A and B. One of them matched one of the ones from B and C. That will give you, essentially, by only ever looking at pairs, you've now identified a whole triad of stars. And then from there, after you have your first set of three, I use this method of reprojecting the catalog and then looking for number of matched stars in that way. So repeat this process. Identify a triad, then reproject catalog, and I would require at least 5 matched stars to stop searching. So full disclosure, that's how I did homework 4. Now you don't have to. If there's another way that makes more sense to you, as long as you're creating some sort of an index of interstar angles and searching it, and you can identify the stars, you're good to go. But this is what I recommend doing. And all of the kind of remaining details I'm going to leave as an exercise to the reader for now. But we can talk about this in office hours if you feel like you're hopelessly stuck. But that's enough to get you started. And after that, the last thing I wanted to talk about is a model. Any questions before we move on? All right, cool. All right. So once the star ID problem is solved, we have an attitude estimation problem. So we will denote the ith star line of sight vector in the camera frame as U, I, hat, camera, tilde, because it is noisy. That tilde means noise. And similarly, in the inertial frame, so the ith star line of sight in the inertial frame, as U, I, hat, no tilde, because it is not noisy. Okay. And so we're going to start to set up the attitude determination problem here, and we'll get next lecture. We seek the direction cosine matrix T I to C, which is inertial to camera. So U, I in the camera frame is T inertial to camera. This could be ICRF to cam. I'm just kind of abbreviating here. U, I. But that's not really what's going to happen. Really, we're going to measure some noisy unit vector, which is T I C U I plus some epsilon. There's going to be some bearing error where epsilon is measurement noise with an expected value of 0. So it's 0 mean measurement noise. Now, here's what's interesting. Because UIC hat and UIC hat tilde. So our ideal camera unit vector and our actual measured camera unit vector, these are both unit vectors. So it must be the case that EI transpose UIC equals 0. Basically, your noise must be perpendicular to your line of sight vector, which makes sense. Your noise is not going to make your line of sight vector longer because it's determined to be a unit vector. It's just going to be basically a rotation on a unit sphere. So I look at it this way. If this your 3D space, come on now, there we go. And if you've got some unit sphere, okay, then you can imagine your before picture might look like this, and your after picture might look like this. Oh, come on now. Try a little harder. There we go. And if you zoom in on this bit and blow it up, then what's really going on here is that your noise is perpendicular to your true unit vector. It's a very small rotation on the unit sphere. So you go from one unit vector to another unit vector. Now this helps us. This actually allows us to simplify our measurement, or a model of our measurement error. So to be clear, this is our unit sphere. So a measurement covariance matrix, which we will use in our derivation, can be built using the QUEST model. QUEST stands for Quaternion Estimator. So Quaternion Estimator. There it is. Okay, so let's think about it this way. UIC hat tilde. This is the actual line of sight vector that we got from our image processing. Well, this is a rotated inertial unit vector. The ith star in the inertial frame rotated into our camera frame, and some noise, which is the same thing as UIC perfect, kind of our ideal measurement, plus some noise. Well, then our measurement covariance matrix is the expected value of noise transpose, right? That's not new. This is exactly what we saw all the way back in lecture, is it up here? Yes, all the way here. Our lecture 11, our measurement covariance matrix is the expected value of noise times noise transpose. Not anything new. This can be approximated as some sigma I squared, which is our bearing error. Talked about bearing error 2 lectures ago. That's our uncertainty in our line of sight direction, times UIC cross, remember the cross product matrix, UIC cross again. So let me go through and work this out. If we do the math, then UIC cross, oh, sorry, transpose, there we go. Goodness me, what is that? UIC cross transpose. If you actually go through and do element-wise multiplication, this is going to be 0, negative U3, U2, negative U1, positive U3, negative U2, positive U1, zeros on the main diagonal. And then you'll get 0, positive U3, negative U2, positive U1, negative U3, positive U2, negative U1, 0, 0. If you multiply this out, you'll get U2 squared plus U3 squared, negative U1, U2, negative U1, U3, negative U1, U2, U2 squared, sorry, U1 squared plus U3 squared, negative U2, U3, negative U1, U3, negative U1, U2, and then U2, all right, U1 squared plus U2 squared, which has a similar structure to, what is that, the inertia tensor? Just notice that. This actually works out to be the identity matrix minus UIC transpose, which we learned all the way back in lecture, I think it was lecture 4, 3. When did we do, boy, I can see that my handwriting is actually deteriorated over the semester. I was hoping it would get better. Sorry. I think it was lecture E. Yep, the projection of a vector onto the plane perpendicular to another vector is this I minus vector vector transpose. That creates a matrix which projects you onto a plane perpendicular to that vector. So that should look maybe a little bit familiar. And that should make sense. Our noise is going to be in a plane perpendicular to our measurement. And so that actually is hopefully not too crazy. We're almost done here. We'll wrap up in a few minutes. Thus, the quest model gives the measurement covariance matrix. I'm tired of this autocomplete. Oh, that's because I have automatic shapes turned on. That's what's been getting me this whole lecture. Sorry about that. Must have been annoying. The quest model gives the measurement covariance matrix. That Ri is approximately equal to our bearing error, which is going to be some angle to which we don't trust our original vector, squared
Paul,
times.
I don't think your shares come back yet.
Oh, I thought I'd finished. Oh, sorry about that. Thank you for bringing that to my attention. I thought I shared. Stand by. Y'all still hear me okay? I'm having technical difficulties here.
Yeah, I can hear you.
Okay, that's good. Somehow, I'm feeling really dumb right now. On my computer, I can't actually access the meeting. I can access, and it's not showing me a way back into the meeting, but also, like, the meeting didn't go anywhere because y'all can still hear me. I'm trying to figure out how to share. Apologies for the interruption here. We'll get this figured out. Weird, I've never had this particular failure mode bite me before. I don't want to leave meeting because I'm worried and shaky. I'm going to try to join the meeting twice, blow things up. We'll see how it goes. Okay. Ooh, I don't like that. Is my voice coming through twice? Or
It's
people just
like
hear me once?
a WebEx is popping up like you're coming through twice, but I can hear you like you're one person. So
Okay. This is annoying, but I'm also like 3 bullet points away from being done with the notes. So we're just going to push through. Here we go. Okay. Can I get verification that you can see this?
Yep.
Okay. Sorry for that hiccup. Get you out of here in a minute. So I3 minus 3 minus UIC transpose. Now, when we're doing our estimation theory work, we're going to need the inverse of our measurement covariance matrix. Remember, H transpose R inverse, all that business. So what we need is R inverse. However, this matrix is rank deficient. So we will use the pseudo inverse. R dagger, which is 1 over sigma I squared I 3 by 3 minus UIC transpose. Thus, we can form the block diagonal matrix. Actually, I think this is just regular. Oh, no, not necessarily. This is block diagonal. And this, sorry, to be clear, this is RI dagger. R dagger would be R1 dagger all the way down to RN dagger. Zeros on the off diagonal. Okay, great. So that is our measurement covariance matrix, which we're going to borrow from in the next lecture when we go through the derivation of Waba's problem and 2 different ways to solve it. But that's pretty much all I have for today. And also, we're having these weird audio issues, which are not fun. So I think I'm going to wrap up here. I'm going to call it. And then I'm actually going to hang up and then re-leave the meeting just to kind of clean this all up. But yeah, I want to thank everybody for coming. And if you want to stick around, we can chat. Otherwise, I'll see you on Thursday.